Start recording. Okay, I got it. So my heart is in anything magnetic fields, right? But although I've worked most of my career, I've been doing theoretical work. The last several years now I've delved into the dark side of observations. Observing magnetic fields is really challenging. I have now I have gained different respect for observers. So so today I'm not going to discuss the magnetic fields in star formation, only maybe tangentially. I wanted to introduce the PASIPHAE experiment. Have you heard about this before? I'm sure some of you have. No. Okay, that's good. That's good. So PASIPHAE is an acronym, as you can see, but it's also a name. It's the name of the Minoan queen. We hope to, with this experiment, we hope to actually revolutionize the way foreground removal is performed for CMB B-mode experiments. So as you know, magnetic fields thread the ISM, but this is good for us, right? That we are trying to study the dynamics of interstellar medium and star formation. But it's an awful foreground for the people, for cosmologists trying to observe the polarization of the CMB, because you see this polarization through the veil of dust, right? So that's what PASIPHAE is trying to do. And let me start with the introducing the team. This is who we are. Other than us in Crete, the University of Crete, and fourth Institute of Astrophysics, it involves institutes from 4 continents, namely IUCAA in India, the South African Astronomical Observatories in South Africa, Caltech in the US, and the University of Oslo next door. And these are our sponsors so far. And this is an aging now family photo. You can tell from the age of Stavros. So, okay, so the aim, I said, of PASIPHAE is to address the thermal dust polarized foreground of the CMB. Right? The problem is that the early universe is not the only source of polarized thermal emission in the microwaves. Right? Because cold, non-spherical dust grains in the interstellar medium also align by the galactic magnetic field, and as a result, they emit polarized thermal emission. Their polarization direction, the polarization direction of that thermal dust emission, though, depends on the direction of the magnetic field, the galactic magnetic field, and has nothing to do with the CMB. And that's exactly where the problem is. Well, the way the dust foreground is actually dealt with by cosmology experiments so far is the following. It's subtracted from maps. Here I'm showing the spectrum in this spectrum, I'm showing all the relevant components, but let's concentrate on the 2 important ones that we care about here, the dust and the CMB. The dust is slightly warmer than the CMB, average temperature of 19 Kelvin, according to Planck. So it dominates the emission at higher frequencies, right? But it has appreciable emission at the CMB frequencies as well. So the way CMB science is done currently is they map the dust foreground at higher frequencies where the dust dominates, and then they scale and subtract this from the lower frequencies where the CMB has appreciable significant contribution. This technique has worked tremendously well, as you all know, right? That's how CMB science has been done, and it works very well for scalar quantities like the temperature, right? So you can detect temperature anisotropies, no problem, despite the presence of the dust, but not so for polarization. So the moment you go into polarization, problems start to appear, and there is. Get rid of that little window. I'm not sure. There it is. Okay. Nope. I don't know how to. Maybe I can move it. I don't know. No, it does not appear on my thing. No big deal. Okay, sorry about that. So the problem has to do with the three-dimensional structure of the interstellar medium, and it turns out to be more severe than initially thought. As our group first pointed out in 2015, you can get a situation like the following, shown here in this cartoon. You have two clouds along the line of sight at different temperatures and column densities, and threaded by different magnetic fields. The cloud that is colder, right, will dominate emission at lower frequencies, and the cloud which is hotter will dominate at higher frequencies. So the polarization pattern, as a result, in this line of sight will rotate between frequencies, trying to trace the magnetic field of the dominant cloud in its case. So this causes problems because it means you cannot just extrapolate, you cannot scale from one frequency to another. There is frequency decorrelation involved, exactly because of the three-dimensional structure of the magnetic field of the galaxy. So this line of sight frequency decorrelation of the polarization pattern has been studied by several groups since, but there has been no consensus about its importance and what the level of this effect is until very recently, that is until 2021, when we had another look at the Planck data. And we actually found evidence of this effect even on Planck, which is relatively low sensitivity than the next planned experiments. So the key to the identification of this effect was that you had to know where to look and how to look, right? And that's where H1 data came to the rescue. That's in two ways. The first is the H1 spectra can be used to identify the locations on the sky where you have multiple clouds, you have structure along the line of sight. And the second way is that high resolution H1 channel maps, as you know, reveal these thin linear structures that statistically appear to be correlated with and aligned with the local magnetic field. So using this fact, Clark and Hensley, back in 2019, they inferred the direction of the magnetic field indirectly, right, using this H1 morphology as a proxy. So we took advantage of this statistical correlation, and we identified locations, lines of sight, pixels on the Planck maps, where the frequency correlation effect was expected to be appreciable, exactly because there was structure and misaligned magnetic fields, magnetic field directions. These locations of these lines of sight make our target sample, pixels, while we also had sight lines that intersected only a single cloud as a control, right, to facilitate the comparison. So we selected pixels from Planck at 2 different frequencies, 353 and 217 gigahertz, in these 2 polarization maps, and computed the difference of the EVPA, the polarization direction, basically. Because the target and the sample, because the target pixels, right, are selected to have a higher likelihood of showing this line of sight frequency correlation, we expected a larger angle difference between the 2 channel maps, the 2 frequencies, statistically larger than the control. And this is exactly what we saw. Here I'm showing the distribution of these EVPA chains, electron position angle, right, the polarization angle, between the 2 frequency maps, the 353 and the 217 gigahertz. And I saw it here for 3 sets of pixels. All the Planck pixels that you can see here in the high galactic latitude sky, we only concentrated right away from the galactic plane. So all the Planck pixels are shown with black. Maybe you can see the black curves here. The control pixels are in blue, no structure. And the orange pixels show this sample of lines of sight where we expect to see this frequency correlation. And indeed, you can see that the spread of the distribution is visibly different. Indeed, this effect that you can see by eye is we tested its robustness against how you subtract the CMB, what algorithm you use to make the maps, the noise level of the 2 sets of pixels, anything you can imagine, removing Planck's systematics with different ways. It turns out that the better you do in removing residual systematics of Planck, the more significant the effect becomes. And of course, let me remind you, right, that the selection of the pixels, the line of sights, has nothing to do with Planck. It's all astrophysical. And not only that, but it turns out that this spread, D, this quantity, correlates, I should be pointing my, so this spread D on the y-axis actually correlates, increases monotonically with the expected misalignment of the magnetic field between clouds along the line of sight, as inferred by the H1 data. So now that we have demonstrated that this effect is actually visible in the Planck data, which was not something not expected because Planck has a relatively small sensitivity, it became urgent to find a way to correct, right, for this foreground. And that's exactly what PASIPHAE seeks to remedy. So the idea is that the same dust grains that emit polarized microwaves also absorb starlight, and in part polarization in the optical of the emerging light. So we can use stars of known distances as lampposts. If we measure the polarization of many stars of different locations, different distances along the line of sight, but known distances, then we can infer the direction of the magnetic field between them and use this information to subtract the dust foreground from the CMB B-mode experiments, including the 3-dimensional effects. This is possible now because of Gaia, of course, right? That has provided billions of accurate distances, and PASIPHAE, which will provide the necessary polarization measurements, stellar optical polarization measurements. And for the first time, we hope, our ambition is to be able to construct a tomographic map of the galactic magnetic field direction in the cold ISM, in cold clouds. The PASIPHAE survey will cover the high galactic latitudes where CMB experiments concentrate, because that's the main science goal. This is the original plan, the first phase of the survey, but we have the ambition to cover the whole sky eventually. We have two locations, two sites that will be taking data. One is located at Crete, the Skinakas Observatory, close to the University of Crete, and the other is in Sutherland, the South African Astronomical Observatory's facilities, so that we cover both the southern and the northern sky. The survey will actually measure several millions of stars in this high galactic latitude sky, and this constitutes, I'm not sure if you realize, this is a huge improvement over the current state of the art, which is shown here. This diagram shows you the number of stars per square degree with measured polarizations versus the galactic latitude. And clearly you can see the galactic latitude, the galactic plane dominates, right, the measurements, because it's driven, this whole business is driven by people like you, right, like us, who care about star formation. So that's where stars are forming. That's where we're looking. But the high galactic latitudes are completely ignored. So we will go up to at least 360 stars, we estimate, per square degree with measured polarizations. And that's a factor of 1,000, right, increase. To achieve this goal, though, we need to have a very strict systematic constraints. So we need to constrain our systematic uncertainties down to the level of 0.1% in polarization fraction. We need this, of course, because at high galactic latitudes, as you know, there is not enough dust. So little dust means little polarization, and as a result, we need to do better in these measurements. To achieve this goal in a large field of view, we have designed and we're building two innovative, unique polarimeters exactly for this survey, that we call WALOPs, wide area linear optical polarimeters. They are based on the very well-tested technology of RoboBall, which is a single short 4-channel polarimeter that has been operating very successfully at the Skinakas Observatory since 2012 and has delivered amazing science. So what WALOPs will do is they will deliver they will expand the RoboBall capabilities into a wide field of view, a quarter square degree. These instruments are actually under development at IUCAA in India, and the southern one is expected to be commissioned in the next couple of months in South Africa. So the survey will begin this year, finally. These are the relevant papers if you care to find out more about the technology of WALOPs. Now, the other thing that we discovered, right, the other thing that is essential to get such a constraint on strict constraint on the uncertainties is calibration, right? To calibrate the polarimeters, as you might know, we use standard stars. We calibrate them on the sky, right? And we have discovered that, unfortunately, the standard stars that are used are nowhere near standard in that level of accuracy that is required, 0.1% in polarization fraction. So we embarked into a large investment of telescope time with RoboBall over 6 years. We collected data, monitoring the polarization of over 120 stars in different, all over the sky, as you can see here, trying to test their stability and how if they can be used as standards with this kind of, at this level of accuracy that is required. And we discovered that lots of the stars, the standard stars that are used nowadays, until now, are actually not standard at all. They are variable and unreliable. The good thing is that we have identified around 65 actually standard stars, and this sample of stars is actually stable and reliable down to 0.1%. This work was led by Dr. Dmitry Glinov, who is located at the University of Crete and the Institute of Astrophysics, and it's now published. You can get it from the paper, or you can obtain the list of standards from the Robopol webpage. So let me briefly then explain how we plan to perform this tomographic polarimetric reconstruction with PASIPHAE data. In this cartoon, I show the situation we are faced with: multiple clouds along the line of sight with misaligned magnetic fields, and stars between them. Each star is affected, of course, by polarimetrically, right, by the clouds in front of it. By measuring the Stokes Q and U parameters, which in the case of, in the limit of small enough polarization are additive, that's important. We want to from the observables, the observed Q and U's, to figure out how much is the contribution of each cloud individually. So we have developed a Bayesian framework. We construct a likelihood function for each sightline, and each cloud adds 6 parameters, 6 unknowns to the likelihood: the distance of the cloud, the mean Q value of the cloud, the mean U value of the cloud, and 3 more parameters that quantify the dispersion, the intrinsic dispersion because of turbulence of this cloud. We float a number of clouds in each sightline from 1 to 5. We explore different models, and 5 is the magic number. That's the upper limit that we expect from H1 data. And we select a number of clouds that best describe the model, with a number of clouds that best describe the data based on the computed evidence. And this is a small animation to show how we evaluate our algorithm on a vast array of realistic simulations. This is a simulated sightline, a quarter square degree, half a degree on the side. It contains 2 clouds, and you can see that if you put them on the QU plane, you start to see clustering. If you use the Gaia distances and you split the Qs and Us, you can kind of see the jumps, right, immediately. And by eye, you can see even the location of the first cloud. But the algorithm is actually pretty efficient and can find the second one. It finds the second one because the dispersion also it contributes, right, in the presence of the second cloud. It contributes through the dispersion of the polarization measurements. So for this case, this is the result. On the left plot, I'm showing the maximum likelihood values for the location of the first and the second cloud. The mean Q and U are in green and purple respectively. You can see them in this plot. For both clouds, I am showing also the 1 and 2 sigma uncertainties with the shaded regions here. The posterior distribution of the cloud distances is shown here, and the blue vertical lines show the true location of the clouds, the first and the second cloud. And the rightmost 2 plots, I show the posterior contours of the mean Q and U for each cloud, with the blue cross being the true value. And as you can see, we can recover not just the Qs and Us, but also the distances of these clouds with high accuracy. And the most important thing, it's based only on polarimetric data and Gaia and distance, nothing else. Now, there's no prior, right? There's no, we don't use dust or H1 or anything else, just from polarization measurements. This software, it's called BEAST-1, is actually available online, and you can use it. I'll come to that. And using this single line of sight software, we have actually embarked, while WALOPs are being developed, into studying an actual 4 or almost 5 square degrees on the sky region using RoboBall. RoboBall is the smaller polarimeter that is already operational. These are the polarization segments that we have measured. It's over 1,600 stars that we measured with RoboBall, one by one. It represents over 150 hours investment, right? But with RoboBall, but with WALOP, it's like half a night. So here is the stars, measured polarizations with the color coded with the distance, the Gaia distances. And you can already start to see that, I don't know if you can, but there are whiter ones that appear to be more horizontal. If you notice, the polarizations are smaller and horizontal, and they are all white. That means they are foreground, right? So we have applied the algorithm, and this is a preliminary movie 3D rendering of the volume rendering of the posterior of the cloud location. The transparency of this cloud is proportional to the degree of polarization, and the color indicates the position angle that you can see here with this circle. You can see that there's a foreground. There's lots of structure, right? Let's put it like that, along the line of sight. There are far away. Oh, by the way, this is logarithmic. This is distance modulus, right? So there are faraway clouds, there are nearby clouds, and there is a dominant screen. This work was mostly the work of Dr. Pelgrins and your own Professor Panopoulou. And it's available, as I said, online. You can go to our webpage, PASIPHAE.science. In the science tab, there is a software tab that from where you can download it and you can play with it. Okay, so say we can get a 3D structure, right? Tomographic mapping of the magnetic field direction. Can we use this? How do we use this to aid CMB foreground subtraction? Well, the obvious question is, PASIPHAE will look at the optical polarization, right? But the CMB is measuring the thermal dust emission in the microwaves, right? The far infrared. So can the two be reconciled? The answer, of course, in this audience is yes, right? You have all seen the Solar beautiful, right, picture correlation between the optical and the thermal Planck polarizations. This diagram also demonstrates the same thing. There is a good correlation. The idea is, right now what happens in this map and subtract scheme is that the modified black bodies model is used per pixel to model the dust emission, right? And it's fitted at the high frequency regime, and then it's extrapolated to lower frequencies where the CMB dominates or contributes significantly and subtracted. Now, what we are proposing to do is instead fit a fancier model where the modified black bodies is fit per cloud, not per pixel, right? If you already know the structure. Including the magnetic field direction as revealed by the PASIPHAE data. And this will lead to, we hope, a much more accurate foreground subtraction, including the three-dimensional effects. Now, going beyond the morphology, because this is just a plane of sky magnetic field direction, right? The Qs and Qs. We can use we can use the dispersion of the polarization segments, right, the measurements, to get to the actual value of the field. So when we embarked, when we started looking at all these things, we started simulating actually the measurements using the well-known DCF method with Rafael Skalidis, and we discovered that the data was not, the method was not accurate enough. We were getting wide fluctuations, wide differences from the simulated data. I mean, the estimated values of the field that we got was completely off. For a long time, we tried to debug it. We eventually realized that the problem was not the method, but was the physics, right, and the assumptions that go behind the DCF. The DCF assumes that Alven waves are the ones that are distorting, right, the magnetic field and in part the dispersion, right, and lead to this formula that you all know and love. We discovered that this is based on equipartition of the magnetic field, magnetic energy and kinetic energy, which is not necessarily true in the regime where the turbulence is supersonic and thus compressible, right? And as you know, in the interstellar medium, nobody would argue that the turbulence is actually alvenic, right? I mean, incompressible. Now, the thing is, if you include the compressible modes, two of them you can see here, the fast and the slow magnetosonic waves. If you make this, if you relax this assumption of DCF and allow for compressible modes, then this in part a tiny little modification of the DCF method, and that is you have to take an extra square root here, right? That's all it takes. Everything else is the same, right? The only difference is that there is a square root. That's what we proposed. We have explored the validity of this small modification in several simulations, and we have found that while the DCF can be wildly inaccurate, this is 3,000%, our method actually gives quite accurate measurements down to 30%. Without much bias. There is the DCF is actually known. This is not something we discovered. That it over predicts, right, the magnetic field, the value of the magnetic field, and this offset can be quite wide. So the idea is now that we have an accurate way to get to the actual value of the magnetic field, and we have the tomographic decomposition where for each cloud independently we have the dispersion values, right, from the PASIPHAE data combined with Gaia. The idea, the final ambition is to produce a map of not just the direction but also the strength of the magnetic field, or the plane of the sky magnetic field. Notice we are missing still the line of sight component, right? But nobody's perfect. No, we are working on that as well. Actually, Vasu is working more on that. Quite an ambitious plan, but we think that even without that, right, the PASIPHAE data, although it's the main scientific question, the main science driver is the CMB foregrounds, right? It will deliver, it will be able to open up new windows and allow us to approach questions such as what is the origin of the magnetic field of the galaxy? Is the magnetic field dynamically important in individual clouds? What is the origin? How important is the magnetic field, the origin of everything? How do you form molecular clouds, right, from the diffuse ISM and so on? And even address the question of the origin of ultra high energy cosmic rays. These are extremely high energy cosmic rays are bent on, but in the galactic magnetic field, but only a little bit. So if you knew the three-dimensional structure of the magnetic field, then you can retrace, right, backtrace to the source. But other than that, the polarization measurements will also contain lots of intrinsically polarized sources, right? Because we have actually estimated that approximately 1% of the measurements are not induced by the ISM. They are intrinsic polarizations either in stellar systems with disks or whatnot, or even extragalactic sources, right? Synchrotron, blazars, whatever, right? That you can see in the optical. And of course, who knows what else? I mean, every time you open a new window of discovery, there are always serendipitous things that come up. So to end, I invite you to have a look at our white paper back in 2018 for more details. Keep updates from our webpage. You can see all the news. But most importantly, there is a cool little thing that I want to show you that you can find on the webpage, and that is if you go to the Science tab again, you see here Science. If you click there, there is a software that you can download and play with it. But also there is this visualization that we have developed, where you can control the view and you can fly through space. We have ported all the relevant Gaia data. The dots are actual Gaia data. These are actual locations of stars, and these are our measurements. And you can see here in 3D, right? This line of sight where we have measurements. It's like a small, tiny little tile on the sky, 4 square degrees. But we have done the decomposition, and you can see the clouds. And if you notice this, the leak pattern shows you the direction of the magnetic field. So different colors for different clouds. You can play with them. It's fully interactive. This shows you the location, the way you're looking at on the galaxy. This is the location of the sun. So let's play this again. There are 2 buttons here. With this one, you can move through space. You can go forward, backwards, upwards. You can set the speed. And this is to control the view, right? Where you're looking at. So I invite you to play with this and give us feedback. I would love to know how we can improve. Thank you very much.